Sorry that the projector's not on. We're working on getting the code to turn the projector on. It seems it's been changed during this week. So I noticed a lot of you are on Piazza, but not everyone. Please go on there and register because we'll do communication through Piazza. You won't hear announcements. So please do that. And one thing I wanted to mention last time is that this is a very diverse class. We have people from different majors, different years. In fact, I thought we'd take a minute just to see what variety we have. I know we have something on the order of 10 freshmen. Would the freshmen stand up in the room? Wow, a lot. All right, yeah. Okay, thank you. We have the sophomore classes as a required electrical engineering class. Some people took it last year, but otherwise a lot of sophomores. All the sophomores want to stand up? There we go. Nice. Okay, now we have, go ahead and sit down. We have some juniors and seniors, I know from other majors, math, econ, and so forth. Juniors and seniors? All right, so we've got several. And I know we even had some graduate students. Are there a couple of graduate students here today? There's one there. Computer science? Okay, great. Good. So the reason for that is this material is actually broadly applicable. So hopefully you'll get a flavor this semester for what kind of applications you might use it for. But in fact, it's used in physics. It's used all over the place, and you'll see that over the years. I think that the Fourier transform appears everywhere. Okay, so you may have noticed I put the lecture notes that I write on the overhead. I put them online. I'm going to use the chalkboard right now. Unfortunately, that means this part won't be up online, but let me use it till we get the projector going. So first, some review. Let's just continue on where we were on complex numbers. We'll just spend a few minutes on that. I wanted to finish off a few things that we were talking about. So we have something called a complex conjugate. Okay, so this, and all this means is you negate the imaginary part of the number. Okay, I may be writing small. Is this too small? If it's too small, raise your hand. I'll write bigger. Okay, so for example, and we use the star to denote conjugate, 1 minus 3i conjugate equals, 5 minus 3i equals 5 plus 3i. Just negate the imaginary part. Okay, you can look, since we talked about a complex plane, you can see what happens to the number in the complex plane. Here's the real part, and here's the imaginary part of the plane. And that number is something like, let's say there's 5 and here's minus 3i. So that number was right here. And the conjugate of it flipped up this way. So complex conjugates flip across the real axis. All right. Now, another way to look at this is that, so it flips across the real axis. If you're thinking of polar coordinates, then we had a magnitude and a phase of the number. And when we conjugated, we kept the magnitude the same, but made the phase negative. So what I'm saying is a e to the I theta conjugate equals a e to the minus I theta. Here I'm assuming a is real. Okay. All right, so two ways to think about it. Negate the imaginary part or reverse the phase. All right. And we can have a couple of rules. If we have two things multiplied together, x times y, when we conjugate them, we just bring the conjugate into each. And one more thing, if we have e to an arbitrary number, let's say a complex number, x, and we take the conjugate of this, then we get just e to the x conjugate. Okay, so these are some rules you can use if you're doing some calculations with complex numbers. Okay, now let's talk about the real part of a number. Okay, so we might say real part of x like this. All right, and of course we know that it's just I'll just do some examples just because we know how to do this if it were using rectangular coordinates. So let's do 5 minus 3i. The real part of that is just 5. The imaginary part of 5 minus 3i equals negative 3. But I'm going to give you now a formula for calculating real and imaginary because sometimes you're not going to just have something so simple as rectangular coordinates and you want to know what the real part is. Okay, so the real part can always be calculated that the real part of x is x plus x conjugate over 2. All right, and the imaginary part then of x is x minus x conjugate over 2i. And we can verify, you can do this as an exercise and see that you get the right answers when you use this way of decomposing a number. Okay, as an example, let's use what we mentioned last time. Let's start with, we have Euler's formula that e to the I t equals cosine of t plus I sine of t. Okay, so for fun, of course we could apply these formulas. And we know first of all, we know what the real part of this is. It's rectangular coordinates right here, real imaginary, right? So let me write out that, of course, cosine of t equals the real part of e to the it. We know that by inspection. But then if we plug in our formula here, we get that equals 1/2 e to the it plus e to the minus it. We can do something similar for sine. Sine t, this podium's in the way for people. I'll try not to write this low next time. Is the sine of t is the imaginary part, e to the it, and I'm just going to repeat that step and say it's 1 over 2i e to the it minus e to the negative it. Okay, and these you might recognize as equivalent statements to Euler's formula where you go in reverse. If you have what we call a complex exponential, if you want to write a cosine in terms of complex exponentials, you can write it this way. And sine can be written as well in terms of complex exponential. In fact, I love these breakdowns because most formulas you learn in trigonometry, and trigonometry had a little too much memorizing for my taste. You can just derive almost all the rules if you just substitute this and carry out the multiplications or whatever you're trying to carry out, and then really simplify, you can derive everything quite easily. Okay. The magnitude, so suppose we want to calculate the magnitude of phase of a complex number, and we have it written in some other way. Maybe it's written in rectangular coordinates. Okay. In general, we can write it that the magnitude is, and then we might use absolute value of x to denote that, is x times x conjugate square root. Okay. And we can check our rectangular coordinates because we know we have a nice geometric interpretation of complex plane. real direction, the imaginary direction, and we know the magnitude should be the distance of that line. So if we have a plus iv as our number, then we can write out the magnitude of a plus iv equals, let's just figure this out, it's a plus iv times a minus iv, that's the conjugate. And we multiply it out, and we get a squared minus iv squared, which equals a squared plus b squared. So we get square root of a squared plus b squared, and that should be the so it all checks out. Okay, and for the phase, for the phase, we would have, again, using the geometry we've got our real part here. So any number has this is the real part of x, and this is the imaginary part of x. And we want to know this angle. And so theta equals the arctan, arctangent of the imaginary part of x over the real part of x. Yes? Sure. Okay, so it's the arctangent of the imaginary part over the real part. Now, there's some ambiguity to the inverse tangent. You can add a pi to tangent and it keeps the value the same. So this might have a plus pi. I'll say this is optional. What I mean by optional is the easiest way to figure out whether you need the plus pi or not. Well, it depends on what arctan function you use. But by inspection, you can decide, should this phase, you see if this number here would also have the same ratio of real part to imaginary part, right? And so then this calculation is going to give you the same answer for both this complex number and this one. But since our definition of magnitude is always positive, then we need to choose the choice of arctan that makes the appropriate. We might have to add pi. If it was this number, we might have to add pi to our representation of space. Does that make sense? I find it easiest to do that by inspection. Just check that your arctan gave you the right one. Yes?
So we don't care about 2 pi's?
2 pi's, we don't care. Because if you put a 2 pi in, it's technically the same phase. It'll always give you the same complex number. Yeah. But pi's we care about, because that makes it negative. Okay, so these two things would allow us to convert from, say, rectangular coordinates to polar coordinates. If we want to convert to rectangular, then we just simply, let's say we have our number represented as A, E, let me make it bigger since it might be small. Polar representation. What we would do is we would let's just look at what we have here. We know that the real part of A e to the I theta, all right, is, well, we know that by Euler's formula that e to the I theta is just cosine of theta plus I sine of theta. So it's pretty straightforward that this is going to be A cosine of theta. So, and similarly, imaginary part theta equals a sine theta. So then that means that we could take x equals a e to the I theta in polar coordinates. In rectangular, it would be equals a cosine theta plus I a sine theta. Okay, so we're done with the, we're going to talk about complex numbers, but now let's talk a little bit more about some properties of functions for a moment before we get into the fun stuff. All right. Odd and even functions. Okay. So we say that a function, so let's start with even. Function is even, or I'll call it a signal. X of t is even if x of t equals x of negative t for all t. What this means is it's symmetric across the y-axis. But we call it even. An example would be t. Something like that. Even. And odd then is if x of t equals negative of the reflection across the y-axis. Okay, there's a negative sign there. Oops, this is a negative here. Two negatives. Okay, negative x of negative t. So what that means is t something like this would be odd. So this means this was a reflection across the y-axis. This is a rotation by 180 degrees. So signal can be even, it can be odd. Now, the fun part is that we can decompose uniquely any function into an even part and an odd part. Right? Sort of like we decompose any complex number into a real part and an imaginary part, added together. We do the same thing for functions. We'll say it's a unique decomposition So what I mean by decomposition is that x of t, for an arbitrary signal, is a sum of two parts, an even part plus an odd part. Even. Odd. And you can calculate those, and it's unique. There's only one way to split it up this way. And you can calculate them by doing the following. X e of t, the even part, is x of t plus x of negative t over 2. And the odd part is x of t minus x of negative t over 2. Okay. So, well, it's not hard to verify that this is in fact even. Just plug in negative t everywhere, you get the same thing back. And that this is in fact odd. Okay. But, and that if you add them up, you get back to x of t. Okay, so that's what we wanted. Any questions? Okay. I do hope we get the projector because I have some other stuff to show you. All right. Let's talk about a signal being periodic. Okay, so we would say that x of t is periodic with period, with a particular period, we call it capital T. If x of t equals x of t plus cap t for all t. So something that repeats. After t, same thing happens again. And it's not hard to show that this would imply that x of t would equal x of t plus, let's say, kt for all t in integers k. Oh, I'm writing too small again. Sorry. Integer k. Okay, so if it's periodic with period 2, then it's also periodic with period 4, 6. I got it?
I think so. It's warming up.
Okay, good.
It's 258. What did it work before? It's never 4 digits.
Really?
I don't know.
All right.
I didn't know you told it.
Good. Well, that's funny because the other 4 digits were the rest of the formula. 258 to the beginning. Okay. Thanks. So, let's see. I'll transfer over to here, if you don't mind. Okay. Check something. All right. Okay, so let's define a fundamental period. Let T naught be the smallest period. Okay, so we said that if you're periodic with some number, you're also periodic with any multiples of it. Well, let's just look at the smallest period. Call that the fundamental period. And we would also call a fundamental frequency is just let's say f naught equals 1 over t naught. So it's just the inverse of the fundamental period. What does it mean if the fundamental period is 0? Constant function. Okay, so a constant function would be periodic with any period, and so its infimum would be 0. I should have said, I guess, when I wrote the definition of periodic behind here, that that we would say it's periodic with period t, where t is positive. Okay, everything. Now I'm confusing you. I should have in the original definition, we require the period to be positive because any function is equal to itself for all t. Okay, so you look for a positive t, cap t, for which x of t equals x of t plus cap t at all t. I'll write it just so I'm not confusing. Let me insert some space here. Okay. Just rewriting what I wrote on the board. Period x of t is periodic with period t greater than 0. Okay, I'm adding that there. If x of t equals x of t plus cap t for all t. If I didn't require cap t to be greater than 0, you could always use cap t equals 0, and this is always going to be true when you say any signal is periodic. So it has to be a positive cap t. However, then when we come down here and we say what's the minimum such cap t, well, if for a constant function, as was mentioned, every positive t would be a period of that function, of that signal. And the infimum then is actually 0. Okay. The infimum of all positive numbers. So if we say the fundamental period is 0, then it's constant. It actually, you could be tricky and construct a function that is not constant and still has fundamental period 0, but you do something very weird. You can't do, if it's continuous, then for sure it has to be constant. Okay. We're not going to deal with all the edge cases of mathematics in this class. Okay, so good. Time for a fun demo. Oh, we're going to look at, let's do some examples of periodic functions. Of course, you know generally what it means to be periodic just from the definition. If you have something that looks like, maybe it's, okay, that's a hand-drawn attempt at a periodic signal. Okay, and the period then would be something like, we see it repeating, assume this is exactly repeating. From here to here is the smallest period. So this would be the fundamental period, t naught, be that distance. Okay. Now, some signals that we know well as examples of periodic signals. Sinusoids are periodic. Okay, so we have, let's say, cosine of 2 pi ft plus some constant. Doesn't matter. What is the fundamental period of this signal? Let's call this x of t. It's not pi because I have a pi there. 1. It would be 1 if I didn't have the f. It's 1 over f. Okay. So the fundamental frequency of this cosine is f. I put the 2 pi there on purpose so that the f represents what we want it to represent, the frequency. Okay. So this t naught equals 1 over f in this case. Okay. Similarly, sine has the same property, right? This is also periodic. Period t equals 1 over f. By the way, am I in the way of your boys here? I think this thing rolls a little bit. Okay. Now, we can also look at sinusoids that have shorter periods by, let's say, multiply the frequency by an integer. Okay, so also cosine of 2 pi f, let's say, k ft. Well, the fundamental frequency of this thing is going to be 1 over kf. But then again, if I don't care about the fundamental frequency, I can make the statement that this is also periodic with that same period as the above. T equals 1 over f. Okay, it's also periodic with t equals 1 over kf, but any multiple of 1 over kf is also a period. The reason I'm pointing this out is because I can actually then go adding up some cosines. Let me do this. Let's take the sum. Some numbers, which will be indexed by k, will be summing k equals 0 to n. A sub k, these are just numbers, constants. Cosine of 2 pi k f t plus, and we'll let these phases be different for each one as well. So we have two sequences here defining the sum, a sequence of numbers a sub k and a sequence of numbers phi sub k. But every term in this sum is periodic with period 1 over f. The sum then will also be periodic. Okay. With period 1 over f. Okay, so we can sum a bunch of cosines together and get a periodic signal. Now, what's more cool than this, that's pretty obvious, is that any periodic signal can be constructed this way. Okay, so by this way, I mean like that. So you can represent any periodic signal this way. Now I'm going to put this in, oh, I said any signal. I should say any periodic. Any periodic signal. I'm going to put this in quotes because if we want to be really picky with the math, there's few ways to interpret this statement. And some ways will have subtle nuances that will restrict certain functions from fitting in this. My statement is that any signal will work. If we define it correctly, then it's true. Any periodic signal will work. The reason it's a little bit ambiguous is because we have to really represent it this way, we have to let n go to infinity, right? So, in other words, if we have a really strange signal, we might need to keep adding more and more high-frequency cosines in order to accurately represent it. And so then you have a limit of functions. When you have limits of functions in mathematics, you have to worry about what you mean by converging. All right. And then under the right definition, under L2 definition, then you can get any periodic signal. Let's say it's bounded. You can get it to converge. All right. So we have a demo of this. This demo was made with thanks to Jennifer Tang. She graduated last year. She took this class a couple years ago and then was nice enough to make this demo. So here's what we're going to do. We have a choice of functions here. This is using Mathematica. Let's look at this one, the parabola. The software sometimes runs kind of slow, so I have to wait. There we go. Okay, so here's a signal. It's a parabola. We can define that very simply mathematically. And what we're going to do is add up a bunch of cosines to try to create this. Okay, so right now it says I'm adding 0, but I'm actually starting with a flat line. That's our 0 frequency. Okay, now I'm going to add one more. Okay, the second plot here, actually I do have. The second plot here is the separate sinusoids that we're going to add together. Okay, and the third one is their sum. All right, so this is what we want to approximate the parabola. So far, looks a little bit like it. Let's add some more. So we add this the third one that just appeared here. Add it in. Okay, let's keep going. And what she's designed is a calculation that will calculate what is the optimal next cosine to add, so that when you add these things up, it starts getting closer and closer to the parabola. Let's keep adding more and more terms. So we've added 10, starting to look pretty good. There's 15. And the more and more we add, the sharper this is going to get. You see there's some approximation error at the edges here because it's curved. Sinusoids are curved. Right? So they have a hard time approximating a jagged edge. Now, why is there a jagged edge here? What I didn't mention was that the original signal, I have a signal of finite duration. But what I explained was we're going to approximate periodic signals with sinusoids. So really what I mean is we're going to look at the so-called periodic extension of this signal. Okay, if you just repeated this with period 2 pi, because you see this is of a width 2 pi, then that would be a periodic signal that we should be able to approximate with sinusoids. All right, and we're doing a pretty good job here. I'll just move up and do more of them. So if I do 60, okay, starts looking very good. Let's do another one here. We'll do, whoops, we'll do the linear. There we go. All right, here's the linear function. Add in some sinusoids. Yeah, it's starting to look linear with one sinusoid. Once you add more, you get it to straighten out. Okay. Again, I haven't explained at all how you calculate the coefficients. For each sinusoid, we need two numbers. We need to know its magnitude and the shift, which I'm calling phase. All right? And behind the scenes, this is calculating what is the best magnitude and phase to add to approximate that function. All right? And actually, today we're going to talk about how we do that. Are there any questions about this? Yeah. That's a good question. Now, if you look at this is continuous, but then again, we're considering the periodic extension. So in reality, this is not actually continuous. Once you look at, what we're really trying to approximate is the periodic extension of this thing. Now, and we see here that, yes, it has a hard time approximating discontinuities, but it's still going to work. If you add more and more, it'll be a better and better approximation. All right, so even for discontinuous functions, it works. Now, this leads to maybe the subtleties of that statement, that you converge to the correct function. Let me add some more here. You'll notice something interesting if you pay close attention. This error at the discontinuity, there's always a big jump right before the discontinuity. And if you carefully went and measured how big that error is, it actually never goes to 0. So you might say, well, gosh, how can I say that if I add enough sinusoids, I converge to what I'm trying to get, this sawtooth function, if I'm always getting an overshoot that's never disappearing? And you'd have to look at the subtleties of what we mean. Really what we mean is that the error as a function of t, you can plot the error as a function of t, and it gets big right there. Here it's pretty small. right? The error would be the difference between this and our approximation, and that's a function. And if you take if you square it and integrate it, we can use that as a measurement of how close the approximation is, the square error, all right? And that goes to 0. So even though the overshoot stays big, it gets very narrow, all right? So mathematically, it's still precise to say, yes, we do converge in L2 to the function we're trying to get, okay? So there's a lot of interesting nuances to look at. We won't dwell on all of those in this class. Because actually converging in, after squaring and integrating, that has a very real meaning for signals. That has to do with the energy of the noise or the power of the noise. And that goes to 0. That means that, for example, if you were listening if this was a sound wave and you were listening to it, the power of the noise that results from this not being exact goes to 0. So if you put enough terms in, this noise won't be audible. Okay. Anyway, all right, let's look at a couple more examples here. Let's do the triangle. Whoops, I need to move that to 0. Okay. Some of these signals, very rapidly, the approximation starts looking good. I mean, we've only done 5, and it's looking pretty nice. Oops. Okay, I'm going to do one more here. The rectangle. So here's a discontinuity, just like was asked about. Let me start this at 0. Okay, so with one sinusoid, you approximate a square signal like that. By the way, the original signal here, it's hard to see. It's 0, and then it jumps up to 1, and then it jumps down to 0. Okay, that's what the signal is we're trying to approximate. And it gets better and better. But still we notice that this the overshoot never completely goes away. It just gets narrower and narrower. Okay? So all right. We have I'm going to do another cool demo in MATLAB. And this, so I have some code here. It's available online that I wrote. What this does is it's actually reading in a real sound file. So I have this sound, this wave sound. I'll start by playing that. Let me do this. Let me get it louder. Okay, so it's just a voice holding an ah sound. So we'll read that into MATLAB and cut out just a short segment of it to get rid of the part where it's, the intro where I'm coming in and the exit. So we have a very short segment here. And what I'm going to do is first just do this. Okay. So I'm going to plot. I have a few plots here. Let me explain what they are. Whoops. All right. So this is a short segment of that sound clip. You can see that it's periodic, roughly. I mean, nothing's going to be exact when you're taking actual measurements of sound, but roughly it looks quite periodic. You see there are roughly, how many periods do you see here? About 4. Okay. Now I don't have this time scale scaled to anything real, like seconds. I wasn't careful with the plots, as careful as you'll be when you do your labs. But What I'm going to do now is the same thing. I'm going to add some terms in and try to approximate this thing. Okay, so if we do just the first term is going to be a sinusoid that has period equal to this window. So in other words, it's going to be a sinusoid that just goes, the sinusoid that goes like this over the course of that window goes. All right. You can tell by the shape of this signal that that is not going to be a very good approximation of anything here. So the best coefficient that we calculate for that is very small. You can't even see it. If you look very closely, found a little bit to add in. That's not completely flat anymore. In fact, it's not going to find, the next sinusoid it's going to do is one that has 2 periods in this window. All right? And again, that's not going to approximate this well either. In fact, it's going to take until, which sinusoid do you think will be the first one where we actually find a substantial component in this signal? 4. So once we get to the sinusoid that has 4 cycles in this window, well, we see that the signal is periodic with period 4, so it might be able to find a good match there. So I'm going to jump straight there. I'm going to go to 4. All right. So what I have, let me show you what the different plots are here. So the first one shows the data in blue, and it shows the best approximation using only the first 4 sinusoids and the constant. Okay, so you start getting something, the green plot. Now this next window is showing the coefficients for those sinusoids. So the first 4, there's actually 5 because constant counts as 0. All right, so the first 5 coefficients are plotted here, and you see they're very small until you get to number 4. And that one's substantial. Now down here, what we're plotting is the shift of that sinusoid. Because remember, to do a good fit, you not only need to know the amplitude, but you need to shift it. Notice this isn't exactly sinusoid; it's been shifted. All right. So this is the shift of each of them. Of course, these ones are basically meaningless because they correspond to very small sinusoids. And then we have a particular shift for the one that we found. So let me raise this number up to something much bigger. Let's get a fit that uses maybe, let's say, 30. Okay, so first of all, the green and blue, there's a lot of overlap between the green and blue, so it's a pretty good fit already. All right. We can look at these coefficients now. And actually, we notice something here. The amplitudes, every 4th one has a substantial amplitude. And the in-betweens, not so much. And again, that comes from the fact that there are 4 periods in this interval. Okay. Of course, once you get high enough here, it starts looking kind of jumbled. And it's probably just because the interval of this window doesn't exactly match 4 periods. And so the actual signal is falling between sinusoidal values, frequencies. Okay, now in this case, let me go up to 50. Just to get a slightly better approximation. So, okay, the approximation's pretty good, almost complete overlap here. And we see something more interesting. We see that the coefficients are all kind of dying off. We're not using very much of these high-frequency cosines anymore. Now, turns out because this is actually this is actually a sequence of data, meaning it's been sampled. Okay, we call this discrete time. This is not an actual waveform that is defined for all points in time. It's only defined at discrete values, okay, when it was sampled, as we looked at last lecture. So if I go high enough, I don't actually need to let n go to infinity to approximate this perfectly. In fact, as soon as I let n go to half the length of this window, by the length of this window I mean the number of samples here, then I will get an exact fit. Okay, so that's what we get in discrete time, is we can do an exact fit at a finite n. We don't have to let n go to infinity. Okay, any questions about this? All right, so okay. I mentioned that that we have names for signals that are continuous time, and we have what we call discrete time signals. For a continuous time signal, the domain of the signal, the independent variable, where t is just all real numbers, right? For continuous time signals, discrete time, we're talking about signals where the independent variable, the domain, is just integers. Okay. So discrete time signals are actually sequences of numbers, and continuous time signals are functions on the real axis. All right. Now, we're going to learn how to analyze both continuous time and discrete time signals in this class, and really they're almost the same. There will be some subtle differences between them. But basically, it's just what we use here, separating signals into cosines and making use of that, is going to be the same in continuous time and discrete time. Often the discrete time signal will come from a continuous time signal that you've sampled, right? So maybe you have a waveform that's actually a pressure wave in air that exists at all points in time, and you have a sensor that actually senses at discrete points in time. Now, by convention, we always assume that the values where you know x in your discrete time signal, where x is defined, are the integers. In reality, you may have sampled a signal every 3 milliseconds, all right? And so the numbers that you've recorded actually correspond to points in time that are 3 milliseconds apart. But by convention, we take that sequence of numbers and we call it a discrete time signal, and the axis just becomes the integers. First sample, second sample, third sample, and so forth. Okay. One more thing I want you to notice, before we move on to actually seeing the formula, how we decompose the signal into these cosines, is that remember there were two numbers to store here: magnitude, which was the AKs, and the phase, which were the phi-Ks. And given these two sequences, then you could go add up the cosines and get your original signal back. Okay. Another way to look at this is that you have, notice that sine, make sure I write it correctly. Notice that if you add a cosine and a sine of the same frequency, that's the same as a single cosine that has this coefficient and has the phase that's the arctan of the two. Okay, so a single cosine with a phase shift can be written as a sum of a cosine and a sine with no phase shifts. Okay, so an alternative way to reconstitute your signal is to convert these numbers into two other sequences. Let's call it I've already used A. Actually, I like C here. into two other sequences, AK and BK, where then x of t is the sum for all k of AK cosine 2 pi ft fkt plus BK sine. Okay, so after performing the correct conversion from these first coefficients to the second one, you can come up with an equivalent way of reconstructing your signal using cosines and sines that don't have phase shifts. I'm only bringing this up because you might recognize the relationship, these two formulas. We have them written on the board somewhere here. This is also the formula for converting complex numbers in rectangular coordinates to complex numbers in polar coordinates, the magnitude and the phase. So I'm just kind of hinting at how using complex numbers can actually simplify the math here. And that's the next thing we're going to do, is we're going to jump straight into the use of complex exponentials.
Is the k, the 2 pi k ft, the same as the counter k?
Yeah. The counter, meaning in the example where I kept incrementing to a higher...
No, see, like from k to 0.
Yes, it's the same k. Yeah, so you have a new term for each multiple frequency. Okay, use complex exponentials instead of sinusoids and sines and cosines. So what we're going to do is, let's first just get some intuitive familiarity with a complex exponential function. Instead of, what this means is we're going to try to write x of t instead as a sum from k, sum over, I'll put the limits of k in a minute. We're going to do a sub, or c sub k. And we're going to do e to the I 2 pi k f t. So instead of trying to decompose x of t into a sum of sines and cosines, here we wrote it one way where we have unshifted sines and cosines, and here we write it where we have magnitudes and phases of cosines. Okay, we've already discussed that these are equivalent. Whoops. This and the previous one. But now we're going to see we can actually use complex exponentials instead. Now, intuitively, this may be harder to understand. Why would we want to do that? Sines and cosines we understand. Why use complex exponentials? The math is going to be much easier, less bookkeeping, easier to actually carry out computations and understand the properties. So let's take the effort to become familiar with this guy here. So here is a graph, a three-dimensional graph of a complex exponential function. Three-dimensional because the horizontal axis is our argument, t. Okay, and the vertical axis is the real part of the value of this function. And coming out of the page at you is the imaginary part of the value of this function, because it's a complex valued function. So, so if we slice at any one point in time, then the plane that we slice there is the complex plane. Okay, we can rotate it. It's exactly the complex plane we're familiar with. So this function here, what's being plotted here is e to the, I'm leaving the real part 0, e to the pi t. No, the I pi t. And we get this very nice looking spiral. Okay. And this is the image I have in my head when I think of complex exponentials. I hope you keep this image as well. It's a spiral, this coil. Why is it a spiral like this? Let me do this. So why is it a spiral? Well, we know from Euler's formula that we could have rewritten this to be cosine of pi t plus I sine of pi t. And remember, the real part, so cosine is the real part. So that's going vertical, and I'm not exactly sure why this, which way the axes are aligned, because this should start at the top. Okay, but if we orient it so that what we're seeing vertically is the real axis, then we should be seeing cosine of pi t. Just take it as a glitch that it's negative cosine. I'm not sure why that is. Maybe we flipped it around. It's because what? Oh, it's those zeros in the middle. Perfect. Okay. So what we see here is cosine, right? And if we then rotated it to look at it actually from the bottom, then we would see sine. Okay, because that would be, we'd be seeing the imaginary part. All right? And so when you combine a sine and a cosine, you get a nice coil. So what we're going to be doing then is we're going to be decomposing signals into sums of these guys. So these are our friends from now on for this course. The complex exponential. Now you might say, if we're dealing with signals that are real valued, because most signals you care about are real valued, there will be occasions for actually wanting to mathematically deal with complex valued signals. And the good news is you can do all the same stuff with complex valued signals. It all works. So we are going to teach this as if signals can be complex valued. But yet the cases you care about are going to be real valued signals for the most part. So why and how are we going to represent a real signal with these coils? Remember, a real signal stays in the real plane. Okay, it has no imaginary part. You can plot a real signal in the same space. It's just never going to come out at the board at you because the imaginary part's always going to be 0, right? So then how do you construct a real signal from these coils? They have imaginary parts. Every single one of them has non-zero imaginary parts. And the good news is that where the imaginary parts will be able to cancel with each other. Okay, you'll be able to add together some of these complex exponentials so that all the imaginary parts cancel, and you still end up with a real signal in the end. In fact, it turns out to work very nicely. And here's how it ends up working. Let's look at what happens when I change the frequency. So here are the frequency parameters right here. Let me just slide it down. Okay, so we see what happens when I change the coefficient here. Coil condenses, it's periodic, just like the sinusoid was periodic. What if I make this negative? What will happen? So let's make it 1 first, positive 1. Okay. What happens if I make it negative? Any ideas? Is there such a thing? Negative frequency? It'll flip, and which means what we'll notice is it is different. So if I look at this one, take a look at which way it rotates. Okay. It rotates if time is progressing this way, right? And the complex plane, to look at the complex plane properly, we would want to, hold on. Cosine, real part is up. So we would want to look at it from, let's see, real part is up, imaginary part is this way. Yeah, we would want to look at it from the front coming towards us. Okay, I'm just trying to orient the complex plane the way we usually draw it. We usually draw it with the real part going to the right and the imaginary part going up. All right? So since real part is this way and imaginary part is this way, you'd want to twist it. I'm not going to be able to do that with my pointer. You'd want to twist it and have it coming towards you. I can do that. So coming towards you like this, and then, of course, it needs a rotation. Okay? And we would be staring at the complex plane, and then this ball would be moving along that line towards us to let t move forward. In fact, I can move t forward here. As time progresses, that's what's happening, okay, to this signal, right? We want to look at the complex plane. Okay, now if I make the frequency -1, then it goes the opposite direction. So it's a sinusoid with the opposite rotation, right? So that gives you some intuition for what a positive frequency and what a negative frequency is in terms of these complex exponentials. Really, it means it makes no difference to us in terms of the real part. The real part's the same for both of these. But in terms of its complex values, these complex exponentials are rotating, and they rotate one way or the other way depending on if the frequency is positive or negative. Notice that if you add two of the same frequency, same but opposite frequency, you can get the imaginary parts to cancel. All right. Any questions about this? The next thing we're going to do is we're going to look at the mathematical formula for decomposing a signal into these components. But I'll answer any questions first before doing that, if there are any. Okay. So we call this the Fourier series. So let x of t, we'll do it in continuous time first. All right, so put that here. All right, make sure I have it. Okay, so we're going to come up with a series of coefficients, and here's how we calculate. Oh, sorry, let me first say, let x of t be periodic. Period t. All right. Then let these coefficients ak, which are going to be our Fourier series coefficients. I keep debating whether to use a or c. I think I'm going to switch to c. ck is going to equal the 1 over t times the integral from 0 to t of x of t, let's say x of tau, e to the negative I 2 pi k over t tau. T tau. Just make sure I did that right. There we go. All right. So we just defined some numbers, a different number for each k because you would do a different integral for each k. You multiply your signal by a complex exponential. You have to remember the negative up there. And you integrate. And that gives you a number. It turns out that number is the coefficient for the best fit at that frequency. So then we can reconstruct x of t that it equals the sum of these ck's e to the I 2 pi k over t t. Okay, so this is the forward Fourier series, and this is the backward one. Backward meaning we're going to come back from our coefficients to our actual signal in the time domain. Okay, so some better names for these are, this is called the analysis equation, and this is the synthesis equation. So what that means is, this one, the synthesis, is the one that we were motivated by in the first place. We were saying, we want to represent x of t as a sum of simple functions. So these simple functions are now complex exponentials. Those are our new best friends. Before we were saying sinusoids with a shift. It's the same thing. In essence, it's the same thing. And so with the right coefficients, we can represent x of t as being a sum of these things at different frequencies. And now we have to do positive and negative frequencies. Okay? And how do we calculate the coefficients? We calculate them using this analysis equation. We resynthesize x of t using the synthesis equation, But to calculate the coefficients, we use this analysis equation. Now, we'll talk more next time about why this works. All right, but for now, this is the equation. All right, let's look at what we would do in discrete time. It's very similar. You may have noticed that I like to write discrete time signals as x of n using square brackets and a different number. I don't like to use t. That's just so that when you see it, you automatically know I'm talking about a discrete time signal. Okay. Let this be periodic. Now, for a discrete time signal to be periodic, it has to have an integer period. Period n. Okay, n is now an integer. And here what we have is that we have c of k equals, it's basically the same thing. Let me make sure to do it right. All right. X of n e to the negative I 2 pi k over n little n. Okay, same thing with a sum instead of an integral. And then to reconstitute it here, this is where there's a slight difference. Whoops, x of n is going to be a sum. It's going to look almost exactly the same. The only difference is, I'll tell you the difference in a second. Okay, it's the sum of these exponentials, but we don't actually have to have potentially infinitely many of these. In discrete time, you don't need more than the number of samples you started with. Okay, so we only really need a sum k equals 0 to n minus 1. That's the real difference between these. For continuous time, notice we had to sum potentially infinitely many things to represent an arbitrary periodic signal. In discrete time, you don't. You only have to sum at most n of these. All right. Now, one thing I want to point out with this Fourier series, if someone gives you Fourier series coefficients and says, give me back the signal, well, you should be able to do it, right? But you need one thing in addition to the coefficients. What do you need in addition to knowing the sequence of coefficients? Because you want to do this. You need to know what t is. Okay, so with the Fourier series, coefficients always need an accompanying t. Otherwise, it's ambiguous how you're going to reconstruct this thing. So if someone hands you Fourier series coefficients and says, give me the signal back, they should also hand you t. And then you can give them the signal back. All right. Any questions about this? I still need to mention another formula, something that'll be helpful to get the homework started. Okay. We have something called an inner product of signals. Now, if you remember, the inner product has a very general definition in mathematics. If you remember vectors, inner products of vectors, let x be a column vector, then you probably remember that if you do x transpose x, that's an inner product. If they're real, that's true. We're going to allow the possibility that they're complex. So if they're complex, you need a conjugate on the second one. Okay, that's an inner product. It means multiply each component of the vector, of the two vectors, and add them up. Right? Oops, sorry. I should have y. Let x and y be column vectors. Sorry about that. Then we say the inner product between x and y is x transpose y conjugate. Okay, there's the inner product. Now, for signals, let x of t be a signal. We want to also know how do we take inner products of functions. Okay, and we're going to give you a definition. of what we will use as the convention for inner products of signals. X and y of t. So x inner product with y, when these are functions, is going to be the integral of x of t times y conjugate of t dt. And so it's a very similar notion. Multiply it at each common point and then integrate it up. If they're periodic, we have a different definition. If x of t and y of t have period t, then we say the inner product, we're going to have a different inner product because otherwise we might get infinity when we do this integral. So the inner product will be 1 over t, integral from 0 to t of the same thing. The last thing I want to say, okay, so there's some inner products. We'll use this stuff next time as we talk about why the Fourier series works. Okay, but the reason I'm mentioning it now, like I said it will be for the homework, is that we have a notion of the energy of a signal. The energy of a signal is going to be the inner product with itself. X inner product with X, the norm in a vector space. Right? So the inner product with itself, which of course is going to equal the integral from negative infinity to infinity, x times x conjugate, we have a name for that, it's the magnitude of x of t squared dt. Okay. So that's the energy for a signal. Now, we have something called power. Sometimes the energy of a signal is infinite. That would be true if the signal is periodic. You do this integral, you get infinity. We still might want to capture something to do with how strong these signals are. And so here we say it's the power of a periodic signal is going to be the inner product. I'm going to represent the inner product of periodic signals with a little t down here, so we know that's a different calculation. Okay. For periodic signals, we have the inner product with a sub t. And so the power then of a periodic signal is that inner product with itself. And that makes sense. It's the average energy per time. Oops, 0 to t squared dt. Okay. If it's not periodic, we can also get power. We take a limit. Maybe I'll write that next time. And I think there's only, I think that's good for now. We'll continue Thursday. No class on Tuesday. But you do have labs starting this week. So please show up to your lab session starting next week.